Hello everyone. My name is Skarleth Motino. I am USRA postdoc at the SOFIA Science Research Center. So today I will present to you a little bit of my research. This is something that actually I did for my PhD thesis, but I will focus in the part of the data analysis, the SOFIA data analysis. And I hope by the end of the presentation you have an idea of how to work with this kind of data. So next slide, please. Okay, so the context for this project was to identify local galaxies, nearby galaxies, that actually can be used as analogs to high redshift galaxies. Why? Because we cannot observe in very great detail high redshift galaxies. So to understand better how the star formation is happening in these galaxies and how these galaxies are changing and evolving over time, it's better to analyze nearby galaxies where we have the star population of these galaxies being formed and actively changing. So for doing this, we need to find galaxies in the local universe that actually can be compared with high redshift galaxies. This has to be small galaxies. Usually, we're looking for irregular galaxies that can have high star formation rates and that we can observe in the UV to the infrared. And then this later can be compared with high redshift galaxies, where the main features of these high redshift galaxies will be shifted or redshifted to the infrared or even the radio wavelengths. So this is the idea of the project. Next, please. So to find these galaxies in the local universe, what we did initially was to feed local galaxies. We used a set of 129 galaxies from Brown et al. 2014, and we feed to the CANDOS galaxies. And from these, we select a set of 11 galaxies. These 11 galaxies are the galaxies that give us the best fit for all the high redshift galaxies that we could analyze. And basically what we found is that these galaxies, all of them were blue compact dwarf galaxies. These are galaxies that are dwarf galaxies, as its name says. And we can find these galaxies in the nearby universe. So next, please. So this is the galaxies that we propose to observe with SOFIA. Like I said before, we can observe these galaxies from the UV to the infrared. We're interested in observing these galaxies in the infrared because we need to characterize the dose distribution of these galaxies. And this is only possible using SOFIA right now. We don't have any other observatory that allows to see the dose for these galaxies. So next slide, please. So we propose to observe these galaxies using Hubble instrument because, sorry, because Hubble allows to observe between the 50 to 240 microns. Hubble presents 4 bands that we can observe. In this case, we want to observe in all the possible bands these galaxies because that will allow us to characterize in a very great detail the SED for the galaxies. Then also I put the link here for the Hubble documentation that explain a little bit more about the data and how to handle the data. Next slide, please. And here we have an example of one of our galaxies. Oh, please. Yes. So, no, next, please, 6. That's it. Okay, so here we have Macarian 1450. In this case, this galaxy, here we are seeing the Sloan bands. We're seeing IRAC. we're seeing SOFIA bands, if you see HOP plus 55, and we also have Herschel data for this galaxy. So this is exactly what we need. We need to have the same galaxy observed in a lot of different photometric bands, because that will allow us to do a very detailed SED of the galaxy. And in this case, this is a very, these are very small galaxies. So we are actually not resolving the galaxy. What we are looking here is to measure the total flux of the galaxy. Next, please. So for doing this, for analyzing the data, I did use HYPE. HYPE is actually a tool that was designed for Herschel data. So the name is Herschel Interactive Processing Environment, or HYPE. And then I put a link for HYPE. The environment allowed me to do to work with the fits maps in a visual environment using an interactive window, or actually I can also do scripts. So I can use a Jython, that is a Java implementation of Python, to do scripts. And basically you can do many things that you also will do with Python in HYPE. It doesn't allow you to use all the libraries that Python has, but for what I needed to do for the photometry, I use HYPE. You can also see that you have different frames. For instance, you have a specific tasks that are already defined in the environment, and these are very useful for doing simple measurements like photometry. Next, please. So this is an example of the photometry measurement. You can see in the image these blue rings. They are a little bit dark. I hope you can see it. So you have three concentric apertures, similar to what Emma showed before to do the photometry. What is important for HYPE is that the units of the map is in Jaskis per pixel. And then you can set the radius of each of these photometry apertures, and you can perform the photometry over a source. And then you're going to produce, for instance, in the right, you will see this plot of the flux that is being added over the radius. So what is interesting here is when we do the photometry, if the background of the source is very noisy, you're going to start having, ideally this goes incrementing, and once that gets to the peak, it will stay mostly flat. But here you see some irregularities in the emission. So this is telling us that the background of this image is very noisy, and probably where the galaxy is sitting in a in a negative continuum. So also this can be done through commands. I put a command in the bottom part, but next slide, please. So what we do is, besides doing the photometry of the galaxy, we also measure the photometry of the surrounding of the galaxy. So we create 6 annular apertures around the galaxy. And what we want to do is to measure the background, because if this background is negative, it means that it's subtracting emission from the source. If it's positive, it means that it's adding emission to the source. So that's why we define the flux of the source as the flux that is coming through the main aperture minus the average of the background apertures. What we're doing is defining all of them the same size. So it's basically a simple average here. This will be the source flux, and then to measure the uncertainties, we also use the SOFIA calibration. You can use a percentage to define the absolute error of the SOFIA calibration. probably it's okay using 10%. Uh, if you want to do be like extra cautious, you can go with 15%. So the uncertainty we define as the square root of the flux of the source times the absolute calibration square plus the standard deviation of the background square. So this gives me the uncertainty of this measurement. And basically with that, we repeat for all the bands and for all the galaxies. And we can create all the data points for the infrared part of these galaxies. Next, please. Here I just put the example of the code for doing this. Is basically handling the SOFIA data maps in Hype. So I just wanted to add the example because if you want to play with it, you can download SOFIA maps and you can completely work with them in the Hype environment. Next. And that's the second part of the code. And you can see but we use the annular sky aperture photometry task to do the main aperture measurement. And also you can see we do the other 6 apertures around the source. So you can check it out by yourself later. Next. And when we do that, previous is 12. Yes, thank you. So when you, no, number 12, please. Yes, thank you. So when you do that, you're gonna produce the emission for each band for this galaxy. And one way to characterize the dose is using black body models. Why we use black body models? Because these are also used for high redshift galaxies. So even though there is a lot of different dose models that are way more complex than using simple dose models, it's good to have the black body models that give us temperatures, because then we can later use this as a reference for comparing with high redshift galaxies. So in this case, using black body models, using a single component of DOS was not sufficient to fit the behavior of the data. So what we do is we add a second component and we fit to the sum of the two components. In this case, I use a fixed dose emissivity as 1.5 because I tried doing different values, but it didn't produce too much difference. So for doing the model more simple, I pick a fixed value of beta, but I'm feeding the normalization constants and the temperatures of these two components. Next, please. And then for doing this, basically we're using a Bayesian inference of parameters. What we do is we work in the space parameters. So we generate a grid of all the possible values that these parameters can use. So basically it's defining a rise of temperatures and normalization constants, but then you combine all the possibilities and what you get is a 4-dimensional data cube that you can find the best solution using the chi-square minimization. You define the best solution, finding the minimal chi-square. Next, please. So you can see here, for instance, all the parameters. Is a little bit moved, but we have the temperatures and then normalization constants. And we have the probability distribution for each parameter that give me the best solution. And you can see in the right side, for instance, the dose model for this galaxy. And from this, we can derive the luminosity. Luminosity is basically an integration of this area. And doing this, having very well defined the infrared emission of these galaxies, we can actually get a very well-defined far infrared luminosity, or some people call it total infrared luminosity. So this quantity is also very important for comparing with high redshift galaxies, because in most cases, for high redshift galaxies, we can only have a single measurement, and we have to assume a temperature and then derive a very uncertain far infrared luminosity. So knowing these parameters for local galaxies that share some characteristics of high redshift galaxies is very important. Next slide, please. Here I'm just showing all the black body models, and then here what we are seeing is also I use the lining package. Lining package is actually an ideal fitting package that was written by Rafael Eufrasio, that is one of my collaborators. So what he does is he implements a fitting package that includes the dose attenuation, and he's feeding from the far UV to the far infrared. So he's able to produce the total SED for these galaxies. And he's implementing the drainingly dose models. So these actually give us the features that the black body is not giving us, because it's giving us the PAH emission in this region. And also we get the stellar emission that you can see in red in the plots, and then the unattenuated or intrinsic stellar emission in blue, and the yellow is the drainingly dose models. So I put the link here in the presentation, but I will share the link of the GitHub repository if you're interested in exploring a little bit more about lining. But basically what it does is feeding all the data that you have from the far UV to the far infrared, and then you can produce a very detailed SED for these galaxies. Next, please. Okay, so this image is not right. I'm sorry for this. I will post the image in the Slack. But what I wanted to show is the star formation history of the galaxies. And I think the image didn't came through in the presentation. So I'm just gonna say with the SED, what we do is generate the star formation history for the galaxies, and we split in 5 time bins. Unfortunately, we don't see the image here, but I promise I will post it in a Slack. And that just allows us to see how the galaxies ensemble in the star population, if these stars are mainly John stars, tipo O or B, or they are all stars. So this allows us to classify these galaxies, saying if they are probably very young galaxies, or they actually have a significant component of all stellar population. Next slide, please. So I will just leave the link of the paper here if you want to check it in more detail, and also the GitHub repository here if you're interested in checking the lining fitting package. And I think I'm gonna stop here.